Welcome to Maths with EJD. Having completed the sub-series on ordinary differential equations, which are divided into IVPs and BVPs, from this video, we move on to partial differential equations. Partial differential equations, that's PDEs. And PDEs, so as far as PDEs are concerned, right, we are going to consider, of course, this is just an introduction to PDEs, right? I think what I should even do is, for the sake of it, just say partial differential equations, right? Partial differential equations, or PDEs for short. That's what this is about. So let's talk about this before we move on. So our ultimate goal is to talk about numerical solutions for partial differential equations. But before we say that, we need to know what partial differential equations are. So PDEs, or partial differential equations, are equations that involve partial derivatives of unknown functions. Whenever you solve any differential equation, your result is going to be a function. When you solve a function, your result is going to be a variable X or Y or whatever you're concerned about. So PDEs are equations that involve partial derivatives of unknown functions with respect to more than one independent variable. More than one independent variable. Okay. I mean, at this point, I think it's important to note that if you have OD, you have ODs, right? And you have PDs. We can compare the two of them together, right? The first thing is that ODs have ODs have only one variable, just a single variable. Then PDs have more than one variable. Okay, more than one variable. Another thing is that ODs, you can represent them as dy dx, or then but uh PDs are represented as, so they are represented by partial derivatives, maybe partial y, partial x, or partial. Okay, it all depends on what you're looking for. Let's say, I think on a general note, we can say partial f, partial x, or partial f, partial y, or partial f, partial z, depending on how many variables you're looking at. Okay. So maybe another thing I want to add is that ODEs are defined for y, probably for y, which is a function of only x. On the other hand, PDEs are defined for maybe f, which is actually a function of x, y, z, and so on and so forth. And that is why, so the derivative is partial with respect to each of the variables you might be talking about. So these are some fundamental differences between ordinary differential equations and partial differential equations. One variable for ODEs, more than one variable for PDEs. So our focus now is on PDEs, like I've been saying. So there are equations that involve partial derivatives of unknown functions with respect to more than one independent variable. Now, still talking about PDEs, right? Um, PDEs are fundamental in describing a wide range, a wide range of of physical phenomena, such as such as heat conduction, fluid dynamics, electromagnetic fields, and quantum mechanics. Quantum mechanics. I mean, many things in real life are not actually do not depend on just a single variable. So many things in life depend on at least it depend on more than one variable. So, and that's why partial differential equations are very useful in describing so many things. So most times when we use ordinary differential equations, it can be seen as some kind of oversimplification or something like that because many situations are dependent on several variables. Okay. But I mean, we're talking about PDE. So, um, for example, for example, the heat equation, the heat equation, which actually talks about how heat flows in an object, maybe a metal bar or whatever. So, for example, the heat equation, which is actually partial U, partial T, is equal to alpha uh nabla squared U. So, I mean, this is the same thing as alpha partial squared U partial x squared. Okay. So this is in one dimension, actually. The heat equation in one dimension. In two dimensions, it will be partial U partial T equals alpha into partial squared U partial x squared plus partial squared U partial y squared. I mean, in three dimension, you just extend to, partial squared u partial z squared. That's heat equation for you. For example, the heat equation, right? The heat equation actually models the distribution of heat, the distribution of heat in a given region, in a given region over time, where U is the temperature. U is the temperature, which we're actually looking for if you solve a partial differential equation like this. U is the temperature, T is time, and alpha is the thermal diffusivity. Thermal diffusivity. So that has something to do with how heat flows in the object, diffusivity. Okay. So that is for heat equation. Another very good example would be the wave equation, like maybe wave in a string or something like that. So another example. So I mean, the reason why this is partial differential equation is because you see, the flow of heat U depends on time and it also depends on space. So it depends on space and time. So T is time, X is space, like that. All right. So we move to another example, right? Is the wave equation. The wave equation and the wave equation on its own part is partial squared U partial T squared is equal to C squared del squared U, which is the same thing as maybe if let's just do it in three dimensions. If you want it in one dimension, you stop at x squared. So this is now C squared. Okay, let me write this. Well, it's better to just go ahead. So you have C squared partial squared U partial x squared plus partial squared U partial y squared plus partial squared U partial z squared. So this is the wave equation in three dimension. So if you want it in two dimension, you cancel z squared. If you want it in one dimension, you cancel y squared. So you have partial squared U partial t squared equals c squared partial squared U partial x squared. But this is three-dimensional. So in case you want it in that way, you can leave it that way. So this wave equation now we actually models which models the propagation of waves such as sound or light. Okay, where U represents the wave function, U represents the wave function, the wave function. Okay, in the case of heat function, U actually represents the temperature, right? But here, U represents the wave function. T is time, T is time, and C is the speed of the wave. Wave speed is the speed of the wave. Okay. A very good example of this is any stringed instrument like guitar, like violin, viola, violoncello, or something like that. So anything that has strings like that, are very good examples of where you can actually study uh, wave, how wave is distributed in the strings or something like that. So PDEs can be classified. PDEs can be classified based on their form into elliptic. So we can have elliptic partial differential equations. We can have parabolic partial differential equations. And we can also have hyperbolic and hyperbolic partial differential equations. Okay. Each of which models different physical systems. Different physical systems. In this situation, we're only concerned about the numerical solution, so we won't go into all these depths. But by the time I'm definitely going to still make a playlist on differential equations. So we are going to take ordinary differential equations, partial differential equations, like not numeric this time around, but in their so we get analytical solutions to them. So that's how I'll really distinguish between elliptic, parabolic, and hyperbolic partial differential equations. So since our focus is on numerical solutions, right? So let's see some of this numerical solutions for PDEs. Now, this is just an introduction. So after now, we'll be taking I'm just going to take two methods and then we'll look at it one after the other. So solving PDEs, interestingly, solving PDEs analytically, solving PDEs analytically is often impossible. It's often impossible, or when it is possible, it is impractical, meaning that the process is more tedious than you can imagine. So it's either impossible or impractical, especially for complex or real world problems. So most real world problems are really complicated. Real world problems. Okay. So analytical solutions are difficult to come by. So that leads us to the idea that numerical methods, numerical methods are used to to approximate solutions to these equations, to these equations. Okay. Now, some common numerical techniques, some common numerical techniques for solving PDEs, for solving PDEs include one, finite difference method. Now this is coming up again. We've seen finite difference for uh numerical differentiation. Then now we are seeing it again. We saw it again for solving boundary value problems. That's one of the methods for solving boundary value problems. So now we have finite difference method. So for partial differential equations. So some highlights. This method, this method approximates, it approximates derivatives using finite differences, just like what we did for BVPs. It approximates derivatives using finite differences. BVPs are boundary value problems. Okay. So for instance, for the heat equation, for the heat equation, spatial derivatives, that's the xyz part, that the squared y, the x squared part. So for instance, for the heat equation, spatial derivatives, so I told you t is time and x is space, right? X, y, z are space. Talk about space. So for instance, for heat equation, spatial derivatives might be approximated, might be approximated as, this partial u partial x. Okay, for heat, it's partial u partial x. So partial u partial x can be approximately u of xh. That's more like ui plus 1 minus ui minus 1. So this is forward difference, I believe, divided by 2h, something close to this. Where h is a small step size, small step size. Okay, so this method is often used. It's often used for time-dependent problems. For time-dependent problems. So that's finite difference method being useful here again, as we see. Now, let's talk about another method which also has the word finite in it. This time around, it's finite element method. So finite difference, finite element. Finite element method, which is FEM for short. Finite difference method is FDM for short. This is finite element method, FEM. So here in FEM, the domain is divided. The domain is divided into smaller subdomains. So these smaller subdomains are known as elements. And the PDE is solved using those elements, right? In FEM, the domain is divided into smaller subdomains, which are called elements. So then the PDE is solved on these smaller elements, on these smaller elements. Okay. For example, in structural mechanics, maybe like in civil engineering or mechanical engineering or aeronautical engineering, in structural mechanics, finite element method can be used to model stress and strain in materials. So you can have it in metallurgical or material engineering too. Okay, that's finite element method. So we can also have what we call spectral methods, which I'm not going to talk about in this series, because we've touched on it somewhat in other places, but not in this particular dimension though. So these methods, the spectral methods involve expanding. It involves expanding the solution. You expand the solution in terms of global functions. That's like well-known functions like Fourier series. Well-known functions like Fourier series or Chebyshev polynomials. Chebyshev polynomials. Okay. Then spectral methods. Spectral methods are highly accurate. They're highly accurate for problems with smooth solutions. Okay, maybe I should change my mind and do one example of this. Spectral methods are highly accurate with for problems with smooth solutions, such as fluid flow, fluid flow simulations. Okay. So these are some things you need to know about numerical methods. Um, so since analytical methods are impossible, so it's very good it's very helpful, like that is, to um to use computation. In conclusion, right? Numerical methods like this are implemented. They are implemented through computational algorithms, and are often used in simulations for engineering, physics, and applied mathematics. Okay. Um, for instance, in climate modeling, numerical solutions of PDEs help predict weather patterns by solving the Navier-Stokes equations, which describe fluid flow, describe fluid flow. All right, so with that, we come to the end of this video. So this is an introduction to numerical methods for solving partial differential equations. In the next video, I'll be taking a dive into finite difference methods. So you want to come along. If you have subscribed, thank you very much for doing that. If you haven't, you want to go ahead and do that right now, because there's a lot you have to learn here. I mean, I have well over 600, about 600 videos, I think, already over 600 videos covering matrices and all kinds of areas, and many more are still coming, because I really mean business here. God helping me. So you want to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then also, let me know how helpful these videos are. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. Afterwards, like and share so that more people can have access to this great learning. Share with your friends, share with your sons and daughters or your relatives who are in schools and they have issues with mathematics. So, till I come away again, keep doing maths right. Bye.